So in this video we're going to be looking at GCSE Physics, some simple graph questions. So if we are presented with a series of graphs that look like this, some motion graphs, first of all these are sketch graphs. It doesn't matter that there's no numbers on these graphs, it's just that you're expected to know what the shapes of these graphs are like. So we can assume that what we're assuming on all of these graphs is that time is on the x-axis, time is going this way, that's why then they're not labelled, because they're all just the same thing, time. However, the y-axis is either speed or distance, can be either speed or distance, so it's important to know which one you're dealing with when you're looking at motion graphs. So make sure you know, is it speed or is it distance? Velocity and displacement are slightly different to these things. They're the vectors, they're covered in my other videos, and we'll talk about those in other videos, so don't worry about those things here. We're just talking about speed and distance. So if we consider some questions now about these, it says which of these graphs above best shows the motion of an aeroplane taking off. So why is it F and B? F and B here? Well, think about when a plane takes off, a plane accelerates. So we expect with the speed time graph for there to be a constant gradient, because the acceleration, that shows that the acceleration is constant and that there is an acceleration, speed is increasing. What would that look like at a distance time graph? It would look like an upward sloping curve. So on a distance time graph, it's the gradient is shown by is showing the speed. So if the gradient is increasing, then the speed is increasing. Whereas on a speed time graph, the gradient doesn't show the speed, it shows the acceleration, and it's showing that it's constant. So this one could be showing the motion of an aeroplane that's just about to take off. A car driving along a motorway, A and G. Why is it A and G? A car driving along a motorway. So A shows speed time graph, and it shows a constant speed. A flat line on a speed time graph is a constant speed, constant positive non-zero speed. The car is just happily traveling along at a given speed, 60 miles per hour, say. And then G, if we look at G, is a distance. So it's starting from some distance, also non-zero, some way through its part way through its journey, and it's just increasing in distance. It's moving forwards, and the gradient shows that it's going at a constant speed. So you've got to match up that this constant speed matches with this distance time graph as a constant speed. They're both showing the same thing, just with different axes. Question 3, a rock falling off a cliff, F and B. Why is it F and B? Well, here F is showing the speed time graph. So the speed is increasing, and it's increasing uniformly, which means that there's a constant acceleration. What gives a constant acceleration? Gravity. So something that's moving under the gravitational influence, in a gravitational field, will be falling at a constant rate. So therefore, let me rephrase that. It's going to be falling with a constant acceleration. So its speed is going to be increasing. And B, again, just like the aeroplane, it can represent the stone falling, because the rate at which it's falling is increasing. Its speed is picking up speed as it's falling down. How about a car approaching red traffic lights, H and C? Let's have a look at H. Yes, its speed is decreasing. It's decreasing at a uniform rate, so it's a uniform deceleration, uniform negative acceleration. C, a slope this way on a distance time graph shows that it's decelerating. Note that it's sloping in the opposite direction to that in graph B, which would be an acceleration, increasing velocity. This one in C shows a decreasing velocity as the gradient decreases. 5, a car which has stopped at a pedestrian crossing. I only. Why is it I only? It's because we're looking for a stationary object. The only graph that represents a stationary object is I. The distance is not changing, it's staying the same, it's staying a fixed distance away from some arbitrary point. Arbitrary mean it doesn't matter which point it is, just measuring a distance and away from somewhere, and that distance is not changing. That distance is staying constant, so it's not moving, it's stationary. Note that A is not showing the same thing because it's got a speed here. Speed, time is not the same as distance, time. And finally, on these graphs, a car initially travelling at 30 miles per hour, which accelerates to overtake a lorry. E and B. Let's have a look at E. So E is at some non-zero speed, and then it accelerates at a uniform rate to overtake something. And B, yeah, it's accelerating. Okay, it's accelerating up. So it's not starting at 0, you see, that's why it's different to F, because it's already traveling at a certain speed and then it increases. The aeroplane isn't moving at first, it's just at takeoff at the end of the runway, and then it increases. So continuing on from question 6, we're on question 7, sketch a velocity versus time graph for a golf ball dropped from the top of the Sky Tower being in Auckland, but it doesn't matter, it could be any tower. Label it golf ball. Well, what happens is that on a velocity time graph, if this thing is dropping through a gravitational field on the Earth, so acceleration due to gravity, gets a nice straight line, first of all, because you've got a constant acceleration. That's just like up here we had the acceleration being a constant for F or E. It's just like one of those ones. That's at the start here, but then it starts to slow down, it starts to curve, just like in C. Sorry, not C, there's a speed, well that's distance. But anyway, the gradient starts to decrease, so that means that the velocity is slowing down. And that's because the air resistance is becoming greater as the thing picks speed up. Air resistance becomes greater and greater, so the acceleration decreases because the resultant force has decreased. It reaches a terminal velocity. Yeah, so the curve flattens out. So first of all you have a straight line, then it starts to curve, and then you get a straight flat line. A table tennis ball dropped from the top of the Sky Tower, label it tennis ball. So this one is going to not reach such a high terminal velocity because its weight is less. And so with its weight being less, then the downwards force is less, and so the acceleration is less, and so the gradient is less, but it still reaches a terminal velocity. Say 4 things that the lines on the graph shows the same for both balls. Start with 0 velocity, accelerate at 10 meters per second squared, or roughly, that's 9.81. Initially, they reach a terminal velocity and then the acceleration decreases to 0.